Hello everyone, welcome to this video. We are group number 1 from division D, and we are here to present you the Booth's algorithm for COA. Basically these are our names, and this will be the structure or layout of this video, in which we will be covering introduction, flowchart, hardware implementation, examples, uses and conclusion. So first of all, let's see the introduction. Booth's algorithm was created by Andrew Donald Booth in 1950. Booth's algorithm is a multiplication algorithm that gives computers a more effective approach than conventional techniques to multiply uh, two signed binary values. It is based on the idea of repeatedly adding or subtracting one of the input numbers, which is shifted left or right by one bit, depending on the value of the adjacent bit in the other input number, that is 0, 1, 1, 0, 1, 1 and 0, 1. It works on a string bits of zeros and ones. It is also used to speed up the performance of the multiplication process. Booth's algorithm, which is still employed in contemporary computer designs, is particularly used for multiplying huge integers.
Flowchart. Here is the flowchart of the Booth's algorithm. Initially, the AC and the Q-1 register will be set as 0. A 1-bit register Q-1 is placed right to the least significant bit Q0 of the register Q. In each of the cycle, Q0 and Q-1 bits will be checked. If Q0 and Q-1 are 1 1 or 0 0, then the bits of the AC, Q and Q-1 are shifted to the right by 1 bit. If the value is shown 0 1, then the multiplicand is added to AC. After addition, AC, Q0 and Q-1 registers are shifted to the right by 1 bit. If the value of the shown 1 0, then multiplicand is subtracted from the AC. After subtraction, AC, Q0, Q-1 registers is shifted to the right by 1 bit. So here is the hardware implementation of the Booth's algorithm. So here is the diagram and the flowchart how it is done. The hardware implementation of the Booth's algorithm requires the register configuration of the facilitated sign multiplication. We name the register as A, B and Q, AC, BR and QR respectively. Q1 designates the least significant bit of multiplier in the register QR. An extra flip-flop Qn-1 is appended to QR to facilitate a double inspection of the multiplier.
Now let us look at an example 7 into 3. The value of A is taken as 0, 0, 0, 0, of Q, which is taken as the value of 3 as 0, 0, 1, 1, Q minus 1 is 0, and M is the binary value of 7 as 0, 1, 1, 1. Now we see that the last digit of Q is 1 and of Q minus 1 is 0. Now following the flowchart, we see that if the digits are 1 and 0, we have to equate A is equal to A minus M. Now after calculating, we get A as 1001. Q remains the same, Q minus 1 remains the same, and M remains the same. This is the first step of the first cycle. Now after this, we have to do an arithmetic right shift following the flowchart. After doing that, we get A as 1100, Q as 1001, Q minus 1 as 1, and M remains the same. Seeing this, we get the last digit of Q as 1 and of Q minus 1 as 1. So from the flowchart, if the digits are same, we directly do an arithmetic right shift. The result comes out to be 1110 of A, 0100 of Q, Q minus 1 remains 1, and M is the same. This was the second cycle. Now, as the last digit of Q is 0 and Q minus 1 is 1, and seeing the flowchart, if the digits are 0 and 1, we have to equate A is equal to A plus M, which is done in the first step of the third cycle. So equating, we get A as 0101, Q as 0100, Q minus 1 as 1, and M as 0111. After this step, we have to do an arithmetic right shift. This gives A as 0010, Q as 1010, q minus 1 as 0. Now as the last digit of q and the digit of q minus 1 is same, we directly do an arithmetic right shift, which is the first step of the fourth cycle and also the last step of the calculation. So the final result comes out to be 0, 0, 0, 1 of A. Of Q it comes out to be 0, 1, 0, 1. Now to get the final answer of this calculation, we have to merge the digits of A and Q, which give us 0, 0, 0, 1, 0, 1, 0, 1. Now if we convert this number from binary form, we get the answer as 21.
Now let's move to a second example, that is 5 multiplied with 7. First of all, we will convert the 5 that is present in decimal form to binary form 0101, that is equal to value of m. Now we will convert the value 7 that is present in decimal form to binary form 0111, that is equal to value of q. After applying the initial value of a, we will get 0000, value of q equal to 0111 and value of q minus 1 equal to 0. The value of q0 equal to 1 and value of q minus 1 equal to 0. Basis on that, we will perform the operation a equal to a minus b. After performing the operation a equal to a minus b, we will get the value of a equal to 1011, value of q equal to 0111, value of q minus 1 equal to 0. After that, we will perform the right shift operation. The value of a equal to 1101, value of q equal to 1011, value of q minus 1 equal to 1. As the value of q0 equal to 1 and value of q minus 1 equal also 1, then we will perform the right shift operation in the second step. Then we will get the value of a equal to 1110, value of q equal to 1101 and value of q minus 1 equal to 1. As the value of q remains 1 and value of q minus 1 also remains 1, then again we will perform the right shift operation in the third step. Then the value of a equal to 1111, value of q equal to 01110, the value of q minus 1 equal to 1. As the value of q0 equal to 0 and q minus 1 equal to 1, basis on that, we will perform the operation a equal to a plus b. After performing the operation a equal to a plus b, we will get the value of a equal to 01100, value of q equal to 0110, value of q minus 1 equal to 1. After that, we will perform the right shift operation. The value of a becomes 0010, value of q becomes 0011 and value of q minus 1 becomes 0. The final result we will get is 00100011. After converting 00100011 binary to the decimal form, we will get the value as 35, which is the final answer after multiplying 5 into 7.
Uses high-speed multiplication in computer processor. It is used for simulation and development of digital multiplier, design of digital filter and signal processing algorithm, calculation of matrix operation in computer graphics, implementation of polynomial evaluation and other mathematical operations.